we started off our discussion about memory, and I mentioned that memory is just considered as a single dimensional array of bytes, and we discussed 1 byte equals 8 bit, 1 word equals 4 bytes or 32 bits. So most architectures address individual bytes, which means that we can, once we have the address of a byte, we can access each individual byte. But the memory address of a word must be a multiple of 4, because we are discussing 32 bits architecture, which means that if we have to store something from register to memory, we have to grab the entire 32 bits data from registers and store it into memory. Similarly, we can grab 32 bits data, which is 4 bytes or 1 word, and we can store it into register. So which means that we are actually accessing entire word. So we need to have the multiple of 4 of address, the byte address. Also we can specify byte number 1, 2, 3, so on. But we need to have, in order to access a word, we need to have the bytes, the address multiple of 4. So as I said, memory may be considered as a single dimensional array of all the bytes, and just like every okay, so let's take another example. If I ask you to construct or develop a map of a new campus, UConn campus, and I ask you to construct 8 classrooms, so you must always have address of each classroom. Like classroom number 0, you can refer it as classroom number 0, 1, 2, 3, and so on. Just like this is the classroom which has an address 305. Okay, so just like every classroom has an address, every byte in a memory also has an address. So this byte may corresponds to our data. It may represent out of CAC, it may represent C, and this may represent S, and this may represent E, and so on and so forth. Okay. To access byte number 0, I need to have its address where this byte is stored in a memory. So assuming that the bytes addresses are starting from 0, 1, 2, 3, and up to n. So this is how the memory is organized, and you can call these 4 bits as one word. But because we cannot express huge memory horizontally in our slides or in any paper, so you will see me expressing or talking about memory as a stack of words, okay, throughout the course. And it is easier to represent memory in this form, just to have enough space. So this corresponds to 0, corresponds to the entire word, 0th word. Okay, so every location is considered as a word. So the next word is starting from the value address, which is 4. Okay, so 4 corresponds to the 4th byte, and it also contains 4th byte, 5th byte, 6th byte, and 7th byte. Yeah, and the next should come 8. I have mistakenly numbering are incorrect. Okay, but you understand what I'm saying? Okay. This is also what we discussed last time. In this 8 bytes memory, we can, of course, if we have to access a particular byte, we can specify the byte address. If we have to access second word in the memory, I would specify the first word, the 0th word is this one, this is the first word, so I would specify the value 4, which is multiple of 4. Okay, so this is 4. If we have to find out what should be the minimum number of bits to express the address of a memory, we can simply determine with the help of the memory size. So here the memory size is 8 bytes. So we can represent 8 bytes with in the power of 2. 2 to the power 3 is 8. So these 3 represents the number of lines, the number of bits we can use to access each byte in this memory. Okay. So if you have 3, you can see that what maximum value you can represent in 3 bits. What is the maximum value that you can represent in 3 bits? 7. So starting from, we can, minimum value is 0. So 0 to 7, there are total 8 values. So we can access each byte in 3 bits only. Then we discussed, like, if instead of having 8-byte memory, if we have 1 megabytes memory, and we perform the calculation in a stepwise manner, like how do we represent 1 kilobytes? So 1 kilo means, in general, we represent kilo with 10 to the power 3. But if I ask you, like, how many bytes you can access with the help of 1 bit? How many bytes you can access with the help of 1 bit? 0th byte and the 1st byte. So you can access 2 bytes in 1 bit, right? Similarly, in 2 bits, you can access 4 bytes, right? 0, 1, 2, and 3. So you can represent a value up to 3 in 2 bits. And the example that we have just seen, in 3 bits, we can access 8 bytes, okay? So 2, 4, 8, 16, 32, 64, 128, 256, 512, and 1024. So 1024 value, which is 1 kilobytes, can be represented in 2 to the power 10 bytes, right? How do we represent mega? Mega is equivalent to 10 to the power 6, right? We can split it into 10 to the power 3, in 10 to the power 3, or in terms of binary, we can write it like this, 1024 times 1024, which is equivalent to 2 to the power 10 times 2 to the power 10, which is 2 to the power 20 bytes. So this is how you can calculate the number of bits required to access the memory with a specific size. And you will see similar kind of question in your assignment, and you may expect to have similar kind of things in your exam as well. Okay. We further discuss, like, we generally refer as kilobyte, but it is actually kibibyte because it is not equivalent to 10 to the power 3. It is 2% larger, which is 1024. Same is the case with other mebibytes, kbytes, and so on.